Today we're going to finally talk about what is called the fundamental theorem of calculus. After almost an entire quarter of studying calculus, we're finally ready for the fundamental theorem of calculus that's going to bring everything we've seen together into one beautiful formula. Let's look at how we're going to get the theorem. So let's take a look at this theorem. I'm going to start with the graph of this guy, just any old random graph. And let's say for a moment we're particularly interested in the area. Let's change colors here. We're particularly interested in the area. Let's see if my graph doesn't disappear on me. There we go. Okay, particularly interested in the area between maybe this point, we'll call that x. This point over here, we'll say that we moved over a width of h, so that's x plus h. And we want the area inside there. So our goal is to calculate this wedge, if you will. Okay, well, we got several ways we can do that. One is to treat it like a rectangle. We're going to kind of cheat. We're going to kind of bring up one side and over so it sticks up a little too far on the right, so we've got this extra space. But then we also missed space. So together the extra and the missed will hopefully, balance out and give us about the right amount. And since that's a rectangle, the area of a rectangle is calculated by the length times the width. And you'll notice that the length here, we have identified that we moved over a distance of h. So the length is h times the height of this guy, going all the way to the top. That actually hits the graph. That's the function f of x. So that's one way we could calculate the area, is treat it like a rectangle, where we have some mist and some extra space, and hopefully it'll all work out for us. Whoops, deleted too much. We'll just leave that. Another way we can calculate the area, though, is to think about it like a subtraction problem. Notice if I took all the area up to the end, up to the x plus h, and let's say I'm going to represent this with a function, a of x. A represents the area from 0 up to the point. So we went from 0 to x plus h, so a of x plus h would represent all of that area. But then we've got the extra area inside that space on the left side. That's extra. So we need to subtract off that extra area. So that's what we're going to do, is we're going to subtract the area up to the point x, and that'll just give us the green area that we want in the center. So that's two ways to calculate the area. One is make a rectangle, width times length. Another way is to look at the area up to the right side and subtract the area up to the left side, cutting it off, leaving just the area we want. Now, because those are both finding the same areas, we can say those are equal to each other, which is why we can divide both sides by h, and we find that the function f of x is equal to the area at x plus h minus the area at x all over h. And where it starts to get kind of fun is when we take that h, that distance between the two, and we shrink it down to 0, where we take the limit as h goes to 0 of both sides. Now what's neat here is that the limit as h goes to 0 of the function is still the function. That's not going to change. But on the right side, what we see is this is the definition of a derivative. The limit as h goes to 0 of a of x plus h minus a of x all over h. We saw that with derivatives. This is the derivative of the area function. I'm going to call it a prime of x. So the function itself is equal to the derivative of the area function. So let's take the integral of both sides. Take the integral dx of both sides, and we end up with the integral of f of x dx is equal to, well, the integral is the antiderivative, so the antiderivative of the derivative must just be the function itself. What we're really saying here is that the integral of the function my U isn't working, there it goes, is the area below. This is the big idea of the fundamental theorem of calculus, is that the integral of the function is the area below the function. In other words, let's do another graph here. We'll do a similar curve, come up, down, around. And if we want the area between this point A and this point B, we want the area between them. The area between A and B, we can take the area from B and subtract the area from A. That is the same thing as the integral. What we're going to say is from A to B of the function dx. So we got a little bit of new notation here. Now on the integral, we see the letters a and b. And basically what that means is we're going to find the antiderivative of f of x, which is the area function. And we're going to evaluate it from a to b. And the way we do that is we take the antiderivative at b and subtract the antiderivative at a. Let's look at how we can do that with some examples. By the way, when we have numbers in the integral, we call that a definite integral. Where we now can see problems like the integral from 2 to 3 of 3t squared dt. Essentially what we're asking with the integral, what we're really doing is, if I look at the graph of 3t squared, looks something like this. We're interested in the area between 2 and 3. How much area is in that part of the graph? That's what the integral is asking. What is the area below the graph? And we can evaluate this. We know that the antiderivative of t is t cubed divided by 3, and 3 divided by 3. And then we don't have to do a plus c because we're going to evaluate it from 2 to 3. And what that means is we're going to plug 3 in, the top one first, 3 cubed, and then we'll subtract, and we'll plug 2 in, the bottom one, 2 cubed. The reason we don't need the c, the constant, anymore is when we subtract, we're going to subtract out the constant. There would normally be a plus c here, and then we would subtract a c here, and that's going to go to 0. So we don't need the constants with the definite integral. Well, 3 cubed, that's 27. Minus 2 cubed is 8, and 27 minus 8 is 19. There are 19 square units between 2 and 3 underneath the curve 3t squared. That's what the definite integral does, is it lets us find the area between these values. Let's try another example. Let's do the integral from 3 to 5 of dy over y. Now, you don't need to draw the picture every time, but just so you know, dy over y, that's 1 over y. That function looks like this. And we want the area between 3 and 5. We want to know how much stuff is in there, under the curve. Well, we know that y is 1 over y is y to the negative 1, which is the natural log of y. And we're going to evaluate it from 3 to 5. Well, that's the natural log of 5 minus the natural log of 3, subtracting those values. And we're going to probably use our calculator to get a round estimate. You can leave it like that, or you can get a number so we've got a better idea what it looks like. That's about 0.5108 is the amount of area between 3 and 5 underneath that curve. Now, something we want to be very, very careful of is when we're doing something like the integral from 2 to 5 of several terms. Maybe 6x squared minus 3x plus 5 dx. Well, we know the antiderivative of 6x squared is x cubed divided by 3. 6 divided by 3 is 2. Minus x squared divided by 2 is 3 halves, plus 5x. And we're going to integrate this guy from 2 to 5. So, when we plug 5 in, we have 2 times 5 cubed minus 3 halves times 5 squared plus 5 times 5. Minus, and now this is very, very important. Just like when we were finding derivatives, I said that minus sign had to be in front of parentheses. When evaluating definite integrals, the minus sign needs to be in front of the parentheses because we are going to have to distribute that negative sign with our work. The most common error people are going to do is they're only going to subtract the first term, not the entire thing. Make sure that minus is going to distribute all the way through. Plugging 2 in, we got 2 times 2 cubed minus 3 halves times 2 squared plus 5 times 2. Now we can do a little cleanup. We've got exponents first, so we've got 2 times 125 minus 3 halves times 25 plus 5 times 5. I'm going to distribute this negative through as I do these exponents. So we have minus 2 times 8 plus 3 halves times 4 minus 5 times 2. Still cleaning up. 2 times 125 is 250 minus 75 halves plus 25 minus 16 plus 3 times 4 is 12 halves, which reduces to 6 minus 10. And just to make life easy right now, I'm only going to do the whole numbers. So that's 250 plus 25 minus 16 plus 6 minus 10 is 255 minus 75 halves. With the common denominator, that's 510 halves minus 75 halves, which is equal to 435 halves. Or if you like the decimal, 217.5. And that is the area under the curve between 5 and 2. Again, very important. Don't miss the step where we distributed that negative through the entire second half. Not just the first part, but through the entire second half. Someone's going to do that on the test. Don't let it be you. One nice consequence that comes out of the fundamental theorem of calculus and the definite integral is the idea of substitution, which becomes easier. Take a look at these two options. We're going to solve the integral from 0 to 5 of x square root of 25 minus x squared dx. And we're going to do this first the old way. Now, the old way starts off with u equal to the ugly stuff. So we're going to make u equal 25 minus x squared. Du then is the derivative of that, negative 2x dx. We've got an x dx, so we're going to multiply by a negative 2 and the reciprocal negative 1/2 to give us everything we need. And then this becomes negative 1/2 times the integral of u to the 1/2 du. Notice I dropped the numbers, the 0 and the 5. That's important with substitution, the old way. Then we took the integral, which is u to the 3/2, times the reciprocal, which is 2/3, times the negative 1/2 that was out front, which is nice because the 1/2s are gone. And now we have negative 1/3 u to the 3/2. Now we can plug in that u that we have. So we have negative 1/3 times 25 minus x squared to the 3/2 power. And now that we've gone back to x, we can evaluate it from 0 to 5. Now those limits come back. We couldn't use those limits with u because they were talking about the x's. But now that we have the x's, we can talk about them again. So we're going to have negative 1/3 times 25 minus the upper limit, 5 squared, to the 3/2 power, minus, and we're going to subtract a negative 1/3, which makes it positive 1/3, 25 minus the lower limit, 0 squared, to the 3/2. And let's see what we get. What's nice is we simplify this order of operations doing the exponents first. We have negative 1/3 times 25 minus 25 to the 3/2 plus 1/3 times 25 to the 3/2. And you'll probably notice that 25 minus 25 is 0. And 0 to the 3/2 is 0, times 1/3 is 0. All of that becomes 0. So we're probably more interested in the right side, which has 25 to the 3/2. The half takes a square root. So we have, the square root of 25 is 5, cubed over 3, which is 125 over 3 for our final solution. Which works. That just basically uses substitution like we always have. And sometimes this way is easier, but most of the time we've actually created more work for ourselves than we had to. Most of the time it's going to be more convenient to employ a new strategy. How about we change the limits also? That way there will be no need to substitute back. So I don't have the problem on my screen anymore, so I'm going to copy it down just so that we have it. We went from 0 to 5 of x square root of 25 minus x squared dx. And we did this substitution before where u equals 25 minus x squared. D is the derivative, negative 2x. We said that means we need a negative 2, so we'll multiply by negative 1/2. And that way we can get this new integral. We got negative 1/2 times u to the 1/2 du. Don't forget the dx was part of that, du. But now we can also take our limits and plug these limits of 0 and 5 into the u equation to find out what our new u limits are. So the top one, when we plug 5 in, we have 25 minus 5 squared, which is 25 minus 25, which is 0. The upper limit is now 0. The lower limit, we have 25 minus 0 squared, which is 25 minus 0. That's 25. The lower limit is now 25. And now we can keep going with this integral. We know the integral of u to the 1/2 is u to the 3/2 times the reciprocal 2/3. Don't forget the negative 1/2 out front. And the 2's are gone, so we now have negative 1/3 u to the 3/2, and we're going to integrate this from 25 to 0. So we have negative 1/3 times 0 to the 3/2. And then we subtract. Subtracting a negative 1/3 is going to make it a positive 1/3. 25 to the 3/2. Notice how much simpler this is going to be. Again, 0 to the power times anything, that's all 0. 25, the square root of 25 is 5 cubed over 3, which is 125 over 3. The same exact answer, but we did not have to substitute back to the other equation and evaluate that more complex equation. So when we have values on the integrals, a lower limit and an upper limit, that we're finding the area for, we simply need to plug those values into the u to find the new limits in terms of u. So let's try another equation. Let's try number 2. Let's try the integral from 0 to 3 of m squared times 4m cubed plus 2 to the 3rd power dm. And you might notice we've got this ugly stuff inside. That's usually a good candidate for our u, 4m cubed plus 2, which means du, the derivative of that is 12m squared dm. So we've got the u in there, but to get the dm, or the du, we need 12m squared. Right now we've got m squared dm. So we'll multiply by 12 and 1 over 12 to make it work out. Now we've got the 12 that we need. So our new integral, with 1/12 out front, is u to the 3rd du. And now we can plug our limits into this function. Plug 3 in for the m. We've got 4 times 3 cubed plus 2. And I'm just going to do that on my calculator. 4 times 3 to the 3rd power plus 2 is 110. That's the upper limit. The lower limit of 0, 4 times 0 cubed plus 2 is 2. So we're doing the integral from 2 to 110. We know that's going to be u to the 4th, multiplied by the reciprocal of 1/4, times the 1/2 out front, so we've got 1/8 u to the 4th, integrated from 2 to 110. Plugging that in, we've got 1/8 times 110 to the 4th power minus 1/8 times 2 to the 4th power. Now I'm just going to type that on my calculator. 1/8 times 110 to the 4th power minus 1/8 times 2 to the 4th power. And it's a nice big number. 1830124 18,301,248. Big answer, not too big of a process. Finding our integral by substitution, using the substitution to get the new limits, and plugging those in and subtracting. Let's do one last problem before I let you go on your own. Problem number 3. We're going to integrate from 0 to 1 of e to the 2z over the square root of 1 plus e to the 2z dz. You might expect with the u, we're going to use the 1 plus e to the 2z, that ugly stuff underneath. Then we can have u to the negative 1/2. du then, the derivative of all of this is e to the 2z dz, which is nice because that's all already in the function. So we've got our u, we've got our du, we're ready to go with our new integral of u to the negative 1/2 du. Now we're also going to evaluate our limits. First, when we put 1 in for our limit, we end up with 1 plus e squared. That's interesting. So the upper limit is now 1 plus e squared. The lower limit, we're going to put 0 in, which becomes 1 plus e to the 0, which is 1. 1 plus 1 is 2. So we're going from 2 to 1 plus e squared. Well, the integral of u to the negative 1/2 is u to the positive 1/2 multiplied by the reciprocal, which is 2. And we're going to integrate it from 2 to the 1 plus e squared. So we have 2 times 1 plus e squared to the 1/2 minus 2 times 2 to the 1/2. And there's not really much simplifying we can do to this. Maybe write it with square roots to make it look a little prettier. 2 times the square root of 1 plus e squared minus 2 times the square root of 2. If we want to get a numerical value, we can type this in our calculators. 2 times the square root of 1 plus e squared minus 2 times the square root of 2. And you get this nice, pretty 2.9643 approximately is the area underneath this ugly curve. So the only really new thing we're doing today is we have values now that we can plug into our integrals. We're evaluating the area underneath the curve. Over the next couple videos, we're going to look at this area concept in a little bit more detail, specifically with the problem of negative areas and what we're going to do about that. And then also not just the area underneath, but maybe the area in between. That's coming up over the next couple days, but right now what we want to focus on is just evaluating these integrals at various points. We will see you in class tomorrow. Come to class prepared with questions after practicing on tonight's assignment.